Hi everyone, welcome. This is week 5, Trinity term 2021 of the Oxford Philosophy of Physics seminar. Very pleased this week to welcome Michael Miller. Michael is an assistant professor in philosophy at the University of Toronto. And this is after his PhD in the history and philosophy of science at Pittsburgh in 2017. Mike works on many things, but in particular the use of mathematics in representing physical phenomena, in particular when the mathematical formalisms break down, and in particular, I should say, quantum field theory. He's written on Haag's theorem, infrared cancellation and measurement, and I think you'll correct me if I'm wrong, Mike, but your most recent paper is worldly precision in philosophical studies, answering the question whether we really need the real numbers in the sorts of applications we often put them to. And today, Mike is talking about a joint project with Porter Williams at Pitt and John Dougherty at the MCMP in Munich on cluster decomposition and entanglement. So over to you, Mike.
Thanks very much. It's a pleasure to be with you, if only virtually. So this is very much collaborative work here, and I'm just reporting for the collaboration. Much of what I'll say here, perhaps the more sensible parts of what I'll say here, I'm indebted to my collaborators for. And of course, the caveat is also in place that the pieces where I appear to be very confused at the end are, strictly speaking, my responsibility, as are any infelicities in the presentation, of which I'm sure there will be some. But those are on me. So I'm going to talk about the principle of cluster decomposition, which perhaps amongst this group, I expect many of you have probably at least encountered in some capacity at some stage. And it's, I think, an interesting principle to engage with conceptually for a number of reasons. For one reason, it's one of these principles that appears all over the physics literature. And when I give a talk on a particular topic, I often like to start with a basic claim that all parties to a given debate would agree with, and proceed from there to things that are more controversial. If you've read a bit about cluster decomposition, you might wonder where I'm going to start. And thinking about that, and thinking about something that everyone would really agree with, what I came up with is this. Cluster decomposition is a property that some theories have and some theories don't have. And that's about as much as one can say, I think, that everyone will agree on. This, of course, barely says anything at all. It does give me an opportunity to say that the particular class of theories that I'll be interested in here are going to be quantum field theories. I'm going to be interested in that particular context of applying cluster decomposition. There's a broader notion of clustering that gets used in non-relativistic quantum mechanical theories as well. And I'm not going to be concerned with those here. We'll have enough on our plate trying to get to grips with what's going on in the quantum field theory case. Okay, so this obviously is a bit tongue-in-cheek. We can say something a bit more suggestive than that to put in your mind what we have, what we mean by this principle. So you may have heard the gloss that cluster decomposition says something like that scattering experiments conducted at large spatial remove from one another should give results which are in some sense independent from one another. So if I set up my scattering experiment at Fermilab and I set out to measure the production cross-section of top quark, say, in a particular energy regime, it shouldn't matter at all for the process of doing that just outside of Chicago, whether or not somebody in Geneva happens to have pushed the on switch at CERN and conducted some scattering experiment of their That's the kind of background intuition that people, or kind of suggestive gloss that people give of what this principle is supposed to be about. But of course, well, let's just jump to the difficulties right away. There's a number of things that make it difficult to be more precise about the content of this principle, cluster decomposition. And let me kind of lay out what I think at least some of those are. This surely isn't an exhaustive list. But like many principles in physics, one encounters diversely expressed motivations for adopting the principle in question, making it part of the theory. So in this case, we've encountered motivations as wide-ranging as that it's an empirical constraint of some sort. So it's some empirical fact about the world that we've got evidence for. In some sense, I'll show you in just a moment what seems to me to be the other end of a spectrum, which is commitment to the view that in some sense cluster decomposition is a precondition on the possibility of physical theorizing at all. And one encounters various motivations between those two poles as well. So that's not particularly uncommon, as also we often encounter. Cluster decomposition sometimes seems to be referred to as a property of different kinds of mathematical objects. So here we'll be talking about clustering as a property of vacuum expectation values, products of vacuum expectation values of products of n field operators in particular. Sometimes it's also referred to as a property of S-matrix elements. This is often the context in which people first encounter the clustering principle. It's also sometimes treated as a property of vacua. That's a piece of this puzzle that Porter has been thinking about in more detail, and I'm not going to address here. But I'll focus on the VEVs and the S-matrix elements a bit later on. So in addition, there's also diverse formalisms in which similar sorts of objects, VEVs and S-matrix elements in particular, people make efforts to mathematically represent, and those come with different mathematical formalisms, and those formalisms come with their own peculiarities and specific issues that require us to pay attention to. In the case of cluster decomposition, in addition to the kind of standard collection of mathematical formalisms we have at our fingertips for the project of interpreting QFT, namely the interaction picture and perturbation theory and the interaction picture, what the Whiteman type axiomatic field theories, algebraic Hag-Kassler, Hag-Araki-Kassler algebraic type field theories. So those are general formalisms for treating quantum field theory. As you may be aware, if we want to treat things like S-matrix elements, we need a scattering theory. In the case of the interaction picture, we're perfectly fine. That's a natural setting in which to discuss things like S-matrix elements. Not so much so for the Whiteman and the algebraic axioms. For those, we need to avail ourselves of the resources of a scattering theory, which we can build inside of that axiomatic framework. In this case, the Haag-Ruella scattering theory. It can be used in both the cases of Whiteman theories and algebraic theories. And perhaps the most slippery philosophically of all of these is that this cluster decomposition belongs to a collection of locality constraints, which many of you will have seen and have engaged in debate about in the literature. Ehrman and Valenti in a relatively recent paper lay out a kind of taxonomy of locality constraints in algebraic quantum field theory in particular, but I think they're sufficiently general to apply really to more broadly in approaches to quantum field theory. So their taxonomy consists of localization properties on the one hand, which they distinguish then from separability or independence type conditions which impose no superluminal signaling or propagation type constraints. And finally, it has a sense as the obverse of non-locality as it arises in quantum mechanics. Okay, so there's of course now in the background a bunch of different philosophical work that's been done on how to think about locality constraints. I think it's interesting that, and perhaps we've just missed it, but cluster decomposition hasn't come along for that particular ride. It's not been widely engaged with in those discussions. And so part of our aim is just to start the project of giving a conceptual analysis of the content of this principle. So there's that standard kind of project in the philosophy of quantum mechanics, the philosophy of quantum field theory, trying to come to grips with the nature of a locality constraint. That problem is going to be in the background here. And so it might seem that really all of these complications are just the normal sorts of complications that are familiar from other foundational issues in quantum field theory. What we want to suggest, or what we've now become kind of suspicious about, is that there seems to actually be something interestingly new going on with cluster decomposition, in addition to these other issues, namely that there's a kind of incoherent tension with the phenomena of quantum entanglement. And obviously, quantum field theory is a theory which aims to represent quantum mechanical systems. Entanglement is ubiquitous in quantum field theory. And if there is a tension between cluster decomposition and entanglement, that's problematic, and one wants some story about what's going on. Okay, so it's really this last piece that I want to build up to kind of saying something about towards the end of the talk. And to do that, what I'm going to do is discuss some of these more standard problems about how we go about understanding the content of a locality constraint like cluster decomposition. And along the way, I hope what will come out is that if we want to get down to the project of evaluating the motivations for actually imposing cluster decomposition, that's going to require that we develop a resolution to the tension with quantum entanglement that we're going to try to raise here. Okay, so I'm going to start by talking about cluster decomposition itself and how it arises first in perturbative theories, how to characterize it in perturbative theories, what sorts of objects it's a principle about in that context. Then we'll talk a bit about Whiteman theories. I won't talk in detail about algebraic theories here. John has done much of the background work to understand how the algebraic type principles are connected up to the Whiteman type principles and the perturbative principles. But that's it's really, the situation there is actually quite similar to the Whiteman type situation. And so for today's story, we won't need those additional details. I'm then going to discuss the connection between cluster decomposition and microcausality to kind of provide a bridge of some sort back to these more familiar discussions of locality constraints in the literature. And it will be in the context of trying to think about that connection, that tension with entanglement arises, and we'll try to do some preliminary work to sort out how to think about that tension. Okay, so here's the scene that we'll be operating in, at least in the context of these perturbative theories. So we're considering a scattering theory where, at least in this context, we want to represent interacting fields. To do that, we take well-defined asymptotic states in the infinite time past and future, which because all of the interactions have shaken out look like free fields. And then we treat the interaction fields as a perturbation around those well-defined free fields in the infinite time limits. Okay, and in the context, this is slightly cheating, but there, in the context of S-matrix theory proper, in 1963, Wickman and Crichton introduced into the literature this principle that they call cluster decomposition. There were related principles floating around at the time, but this is the first cluster decomposition principle recognized in the literature concerning S-matrix elements in particular. And the way they characterize their project is as giving an attempt to identify a condition which every physically meaningful S-matrix needs to satisfy over and above standard constraints like Lorentz invariance and the familiar principles. Here's what they say in terms of motivation. The conditions we wish to impose derive from the idea that the interparticle interactions are of short range. Therefore, the outcome of a scattering event involving two particles that are close to each other at some time does not depend on the presence of other particles very far away. To dramatize the situation, we may say that the presence of particles on the moon must not affect the outcome of events in a bubble chamber on the Earth. So obviously this is sounding a fair amount like our gloss in terms of our scattering experiments at Fermilab and CERN. What's added here, importantly, is that they characterize what they're trying to get at in terms of the interparticle interactions and their short range with respect to distance. Okay, so that's how this principle gets into the literature initially. I hope it's fair to say that it gets kind of reified as a central structural feature of quantum field theory in Weinberg's quantum field theory textbook volumes. And for Weinberg, cluster decomposition plays a significant role in establishing the inevitability of field theory. And in some discussions, not in the textbook, but in conference volumes and things like that, Weinberg's really expresses the view that cluster decomposition is a really fundamental structural principle that characterizes the content of QFT. He seems to think of it as more important structurally or somehow more primitive than microcausality. Whether or not one can make good on that sort of claim is not a challenge we're going to take up here. Okay, so here's what Weinberg says. This, I think, is where the Fermilab CERN gloss comes from. It is one of the fundamental principles of physics, indeed all of science, that experiments are sufficiently separated in space have unrelated results. The probabilities for various collisions measured at Fermilab should not depend on what sort of experiments are being done at CERN at the same time. If this principle were not valid, then we could never make any predictions about any experiment without knowing everything about the universe. So just note at this stage that the kind of motivation that's being expressed here is rather different than the one that Wickman and Crichton introduced concerning the short-range nature of the interactions. Obviously, there's connections that one might try to develop, but you can see that we've got this kind of interpretive problem now of like, what exactly are we trying to say with the content of this principle? What should we take it to be? I've included others here just to kind of to illustrate the breadth of motivations that get expressed for adopting the principle. I'm not going to read all of these out in the interest of time, but for example, Haag in his local quantum physics book focuses on the correlations between quantities decaying with distance. Strokey is particularly focused on the interaction strength or force between clusters. Streeter and Whiteman are explicit that they say that the physical meaning of the cluster decomposition property is that when two systems at points x and y become separated by some large space-like distance, the interaction between them falls off to 0. So like any locality constraint, you can go through the literature and find quite diversely expressed motivations for adopting that kind of principle in question. Let's just start trying to say something mathematical about what we take the content of the principle to be. Okay, so we'll start with the S matrix, and then we'll get to other statements involving other kinds of objects in short order. So the S matrix is defined such that it's the amplitude for an incoming state alpha to evolve into an outgoing state beta. So if we specify some particular particle content alpha, and then we can ask our theory, what's the probability for scatterings to occur, which yields in the outstate the state beta, okay? And the S matrix encodes that information for us. So roughly speaking, the S matrix, we want to define a notion of cluster decomposition, which is satisfied if we take distant processes, alpha goes to beta and alpha prime goes to beta prime, let those processes unfold far apart from one another, okay? What cluster decomposition says is that those should factorize into two independent amplitudes. Okay, so the process alpha alpha prime goes to beta beta prime should factorize into two independent S matrix elements, one for alpha goes to beta, which is unfolding it spatially far separated from alpha prime goes to beta prime. That's the intuition we want to capture. To make this more sharp, and in particular to say what we mean by the arrow when we go from left to right, we need to recall some elements of perturbative scattering theory. Okay, so the basic ingredients of scattering theory are a Hilbert space of asymptotic particle states and a unitary operator on that Hilbert space, whose elements are going to be the scattering transition amplitudes. Throughout, we're going to stick to the example of theories with a single spinless boson field for simplicity. All of this can be generalized for additional particle species, additional with the addition of spin and so on. In this case, though, the one we'll be concerned with, the Hilbert space is spanned by mutually orthogonal elements of the form P1 through Pn, where those are spatial the spatial parts of the momentum vector of and particles, and it's symmetric in the PIs. Okay, so since these vectors span the space, the operator S is going to be fully determined by its action on them. Okay, so if we know these guys, we know the full S matrix. We usually work in the basis of the Hilbert space consisting of momentum eigenstates, which is obviously convenient for a number of different reasons. But if you think about the way I've been talking already, this is going to complicate the task that we've been given. Momentum eigenstates don't have well-defined positions, obviously, and so we can't directly say that some states consist of widely separated clusters of particles. Okay, because there's not well-defined positions to the momentum eigenstates in which we're expressing our states. So we need to do this indirectly with a translation, a spatial translation operator. And so let's assume our space of states admits a unitary representation of the group of spacetime translations under which the S matrix and the vacuum are invariant. That is, we're going to assume that for some vector, we have a unitary operator T of A on the Hilbert space, and this collection of operators satisfies the kind of obvious properties that we want from a translation operator that acts trivially on the vacuum and commutes with the S matrix. Okay. In the case of our single spinless boson field, the collection is generated by the momentum operator, where this P now is the form momentum of a particle with spatial momentum P vector. Okay. And the translation operators give us a way to understand distance scattering processes without appeal to non-existent positions for momentum eigenstates. So what we can do, for example, if we've got a state P1, P2, that representing a configuration of two particles, then for a spacetime vector A, the state that we get by acting with this operator T2A is one which represents a configuration in which the particle with momentum P2 has been displaced by A spatially. Okay, so this allows us to express spatial separation without it, while still working in a basis of momentum eigenstates. So obviously we can generalize this. We don't just need two configurations of two particles. We can do it for any element of the basis that we like. So for clusters consisting of spatial momentum P1 through Pn and Q1 through Qm, we can define a translation operator which moves all of the here Q guys over by any amount that we like. Okay, and that's what's shown here. And leaves the P guy, the P cluster where it is. So now we've got the tool to say precisely what we mean by this arrow where we went from the in state alpha alpha prime to the out state beta prime, beta beta prime, and then spatially separated them, which wouldn't have been a well-defined notion because they're momentum eigenstates. But if we do it with the action of the translation operator, we can make sense of this notion. Okay. So, well, just to recapitulate that. So, so while we cannot say that the cluster of particles with momenta pi is some particular distance from the cluster of particles with momenta qi, we can draw the clusters arbitrarily far apart by applying the relevant translation operator for some sufficiently large vector A. Okay, so we're trying to capture the intuition that the S-matrix clusters, if amplitudes for distant scattering processes are independent. Now we know that this means that the matrix elements of that we get by acting with the translations on the S-matrix are products of the matrix elements of the S-matrix restricted to each cluster. So that gives us the tools to say at the level of perturbative scattering theory, what people have in mind by cluster decomposition. An S matrix satisfies that property if for all 1 to n and 1 to s running 1 to n, we have that the action of this translation operator on the S matrix element for the in state with all of the guys together and the out state with all of the guys together in the limit where we let the translation get really large, factorizes into the S matrix element for the two clusters separately. Okay, that's a precise way to say this arrow goes over between the factors, between the original S matrix element and the factorized S matrix element that we had before. So I couldn't leave this out since John is a stickler for these things. So strictly speaking, this definition is incomplete because we haven't specified the relevant topology in which to take the limit, and obviously the limit may exist in some topologies but not others, and so an S matrix may be clustering with respect to some topologies in which one goes about taking the limit but not others. These nuances I'm not going to be concerned with here. So one broad class of clustering S matrices arises from Hamiltonian dynamics with a perturbative interaction of sufficiently short range. So in a theory of this kind, the S matrix can be re-expressed in terms of an interaction potential V, and clustering we can therefore make into a condition on the nature of that interaction potential. So the relationship between V and the S matrix makes the resulting necessary condition on V somewhat unwieldy, but there's a simpler sufficient condition on V that's easily satisfied that Weinberg identified. So formally speaking, the S matrix implements time evolution from the past infinity to future infinity, where this t0 guy is the unitary operator implementing time evolution from t0 to t, as is, I hope, familiar. In the case of a perturbative interaction, where the Hamiltonian is of the form h equals h0 plus v for v sufficiently small, we can work meaningfully in the interaction picture. In the interaction picture, we can formally solve the differential equation defining that time evolution operator to give us an expression for the S matrix in terms of time-ordered exponential of the interaction potential. So because the S matrix can be written as a function of the interaction potential, cluster decomposition can be reformulated as a condition on V, naturally. The complicated time dependence of the time-ordered exponential and the interaction potential makes this reformulation a bit difficult to execute. What Weinberg identified is a simple sufficient condition for an interaction potential to give rise to a clustering S matrix. Okay, and moreover, it's relatively easy to combine this condition with constraints like Lorentz invariance and to kind of compare the interrelationships between Lorentz invariance of the interaction potential, Lorentz invariance of the S matrix, and this condition on V. So consider the creation and annihilation operators, which take a state with, say, n particles and add and yield a state with an additional particle, or take a state with n particles and remove a particle, respectively. So multi-particle states give an orthonormal basis of the Hilbert space. And so any operator on H is going to be a linear combination of creation and annihilation operators. So what that means is for some family of functions, we'll call them the VMN, we're going to be able to write the interaction potential in terms of the creation and annihilation operators and this family of functions that whose form we've left unspecified at this point. Okay, so intuitively, an interaction is going to cluster. Note now that I'm talking about an interaction clustering. This is one of these sorts of changes that in terminology that occur in the literature. If it is a function of interparticle distances and it dies off when any of those distances is large. So the former condition implies that the VMN have to be proportional to a delta function that enforces overall momentum conservation. And this just drops out of the kind of combinatorics of the creation and annihilation operators. And algebra of delta functions. But if momentum is conserved among any subsystem of particles, then sending that subsystem to infinity is going to make no difference to the strength of the interaction potential, likely violating the second condition. There's nothing to enforce it. So an interaction potential, we're going to say clusters, if for any n and m greater than 0, the VMN, those coefficient functions with respect to which we're expressing the interaction potential, can be written as an overall momentum conservation delta function multiplied by some new functions whose form we don't care about, except that they don't contain any additional delta functions or derivatives of delta functions. So another way to gloss that is that the interaction potential is going to satisfy cluster decomposition just in case the VMN can be written with only one overall momentum delta momentum conservation delta function. So that gives us a test. Give me a interaction potential, and I can tell you whether or not it's going to yield scattering theory. Any interaction potential that clusters in this sense gives rise to an S matrix that clusters in the sense of the above definition. So this is a sufficient condition on the interaction potential to yield an S matrix that clusters in the sense of clustering relevant to the S matrix. Okay. So this turns out to be a completely non-trivial requirement, but the reformulation I just gave in terms of the interaction potential makes it easy to construct clustering S matrices. You just have to make sure that you don't plug in anything into the interaction in terms of delta functions beyond the one momentum conservation delta function that the sufficient condition allows. So here's an example of a way to violate cluster decomposition. You can violate it if you make the interaction potential sensitive to the number of particles in the universe, say, that will break cluster decomposition. And this is actually central to why Weinberg thinks that cluster decomposition pushes us in the direction of a field theory, but that's probably a story for another day. So here's an interaction potential that we can write down. It's got our one overall, momentum conservation delta function, some functions h, and those h's are stipulated to satisfy this constraint. And that condition makes it such that the interaction is Hermitian. The integration measure is chosen such that the expression for the potential will be Lorentz invariant just in case those H guys are Lorentz covariant. And the S matrix, though, resulting from this interaction doesn't satisfy cluster decomposition. Here's why. If there are two incoming particles, then they're going to elastically scatter. But if there's a third incoming particle, no matter how far away it is, no particle is going to interact with any other one. Okay. So any Lorentz covariant H will show that Lorentz invariance doesn't imply cluster decomposition. Any Lorentz variant H shows that cluster decomposition and Lorentz invariance can both fail. Yeah. Good. So let me just see. An interaction potential can lead to a clustering but Lorentz variant S matrix, and there are two ways for that to happen. If those tilde VMN guys aren't Lorentz covariant, then the S matrix generally isn't going to be either, for example. But even if they are Lorentz covariant, the S matrix may not be. So a Lorentz transformation may swap the temporal order of space-like events, in which case the time-ordered exponential defining S will introduce a commutator of V of t at two distinct times, and that commutator generally won't vanish, so it will change the S matrix. Okay. So I think I'm going to skip this example in the interest of time, because I think we've got enough of this piece of the puzzle on board. But before we turn to the issue of entanglement, I think it'll be helpful just to show you the way these notions look in the Whiteman and algebraic type theories equipped with a Hogg-Ruella type scattering theory. So in the Whiteman case, the state is a normalized vector in a Hilbert space H carrying a continuous unitary representation of the Poincare group. Fields are represented by operator value distribution subject to a number of conditions that we're not going to be concerned with here. A Whiteman theory, the details aren't important here, modulo those things that I'll emphasize, but I just want you to see it. So a Whiteman theory is clustering if, and now we get a similar looking condition where what we've got up top is a product, the vacuum expectation value of a product of n plus m distinct space-time points, and that's got to factorize into the two distinct, the endpoint function and the endpoint function respectively, in the limit where that spacing A becomes large. Okay, so in this case, note what's really critically different between the notion of clustering that I gave you at the level of the S matrix is that this is a statement about different sorts of objects. This is a statement about vacuum expectation values, not about the S matrix itself. Okay, and same caveat is in play concerning the topology in which we take that limit. Okay, so we get a natural notion of clustering in Whiteman type theories. Similarly, in algebraic theories, I won't show you how it goes there though, but they're in terms of vacuum expectation values, and they're analogs rather than S matrix elements directly. So to formulate cluster decomposition at the level of the S matrix in either of those theories, we need to put scattering theory inside of these axiomatic frameworks. Hog-Gorilla provides us with the way to do that. So in that context, the ladder operators for incoming and outgoing states are the ladder operators of the interacting Hilbert space at early and late times, respectively. And we're going to assume that the space of incoming scattering states coincides with the space of outgoing scattering states, and in particular that these coincide with the interacting Hilbert space appearing in the Whiteman axioms. So what essentially matters here for our purposes is that we can take an expression for the field operators and invert it to go back and forth between our field operators and our creation and annihilation operators. And to obtain the asymptotic ladder operators, we just need to take the small or large time limit of those of the expressions for the intermediate time ladder operators. So once the existence of the asymptotic Hilbert spaces is secured, we get the existence of the S matrix pretty much directly. And its space-like clustering follows from the space-like clustering of the vacuum expectation values of the vacuum state, or the vacuum state, excuse me. So put it another way, we've got a notion of clustering in Whiteman type theories. Similarly, in algebraic type theories, they're most naturally expressed at the level of vacuum expectation values. But from other central features of those theories, what we get back is a notion of clustering at the level of the analog of the S matrix in the Hog-Gorilla scattering theory that we put inside of the either of those axiomatic frameworks, which has to be satisfied if clustering is satisfied at the level of the vacuum expectation values. Okay, that guarantees that it's satisfied at the level of the S matrix. Okay, so good. So that took just slightly longer than I was anticipating, but now I want to get to this issue of trying to make the content of cluster decomposition precise, being complicated by factors other than just these kind of standard background issues that we have at the foundations of quantum field theory. What we've seen is that John has done a lot of hard work to identify all of these different expressions, how they're interrelated with one another, And while these formalisms are expressed in mathematically distinct ways, conceptually, the property of clustering that's being tracked mathematically here is pretty much uniform. Well, maybe that's too strong, but there's a close conceptual similarity between the property being expressed in each of these different formalisms. We can do it at the level of vacuum expectation values. In each of the cases, that carries over to a property that obtains at the level of the S matrix itself. Okay. So that's the hard work of kind of piecing together what the mathematical expression of this principle actually is in the literature. Now we want to get to the task of, really thinking seriously about what sort of motivation would be a good motivation for adopting the principle. How should we understand it as a locality constraint, and so on. So you might think that to make progress on the locality piece of the puzzle, we can just copy paste our work from other debates about locality constraints already there in the literature. And I think something like that will eventually be true. I think all of that work is going to turn out to be helpful here. But there's an obstacle that crops up. So here's what Bain says about this. So he says that cluster decomposition serves the same purpose for the S matrix as microcausality does for fields. Both are locality constraints that prohibit causal influences from propagating between space-like separated regions of spacetime. Here we get a distinct locality type justification from the others that have been expressed so far for adopting cluster decomposition. Moreover, microcausality of fields is a sufficient condition for the S matrix to satisfy cluster decomposition. And he's talking about this now in the context of perturbative scattering theory. So let's consider the argument that Bain has in mind. And I'm not going to go through all of the details in the interest of time. I just want to get to the upshot. But if you assume that you have microcausality at the level of the fields, you can consider the n plus n point function again, just as we were looking at in the Whiteman case that we considered earlier. Move the x's, the spacetime arguments of the x's, far away from the spacetime arguments of the y's using our translation operator trick. Then you can use that to show that the assumption of microcausality then allows you to split up the time ordering that occurs in the vacuum expectation values. The time ordering is crucial here because at the end of this process, we're going to want to plug this whole apparatus into the LSE reduction formula. And if you grind through what is just algebra, what you find is that you get exactly what you want, which is translation invariance, or you can apply translation invariance as a vacuum to get exactly what we want, which is that these vacuum expectation values, on the assumption that we have microcausality factorized into the two, the n and m point function respectively. Okay. So that shows that microcausality implies clustering at the level of the vacuum expectation values in the perturbative context. In the perturbative context, we just started at the level of the S matrix. What we've just done is gone back and shown that in the perturbative context, you can start at the level of vacuum expectation values and get a notion of clustering, which once you apply this result in conjunction with the LSE reduction formula, allows you to establish that microcausality implies cluster decomposition at the level of the S matrix as well. Okay, so this leads us to the tension that I just want to end by talking about. So here's what I've been worried about, and I still don't know the right thing to say about this. So I'm very curious to discuss this with all of you. Let's just take some particular S matrix element for some particular initial and final state, and let it be an S. Let that be the S matrix for some particular incoming and outgoing state, and consider the following collection of claims. Microcausality obtains independently of the particular matrix element that we consider. It doesn't care anything about what matrix element we happen to be talking about. It's a property of the field operators. Microcausality implies cluster decomposition independently of the particular SFI that we consider. So we just gave an argument for that claim. In the perturbative context, and nothing seems to change in the others. Whether or not cluster decomposition obtains depends on which matrix element we consider. Okay. In particular, if the initial state happens to be entangled, then SFI does not satisfy cluster decomposition. Okay. These three claims cannot all be true. You should be wanting more information from me about why you should believe three. I haven't given you an argument for three. All I can give you at this stage is kind of intuition that I certainly deeply have. I won't speak for the others at this stage, which is that it's unclear that whatever of the given physical motivations that people express for cluster decomposition, you should expect it to obtain if what you feed in is an in-state that happens to be entangled between what eventually become the two different clusters. Okay, we haven't considered a situation like that here. We've made some efforts to actually work out what will happen in that case, but it's technically challenging. There's more work to be done there. But for now, let's just take three as a kind of ansatz and work out what could be going on with this collection of claims. They all of them together can't be true. I've given you pretty good reasons to believe one, and I've given you seemingly okay reasons to believe two. But here's an observation about two. In any of the approaches that we've considered, perturbative, Whiteman, algebraic, doesn't matter. The demonstration that microcausality implies cluster decomposition at the level of the VEVs is completely general. If the fields up, if you have microcausality of the field operators, then the endpoint functions are going to satisfy cluster decomposition. Okay. There's no tacit restrictions going on in the background when we gave those arguments. But now in each of the formalisms, the argument that this implies that cluster decomposition at the level of the S matrix does tacitly introduce specific assumptions about what the in and out states of the S matrix being considered actually are. When they're available, what those arguments show is that the matrix elements satisfy cluster decomposition in the very special case where the in and out states consist of momentum eigenstates. That's what scattering theory is rigged up to be able to give us information about. And with spins that are not entangled, assuming spin is even considered, we haven't even considered spin here the whole time we've been talking. Okay. The question we have in the back of our mind is, what if you want to know the answer to the question about what happens if the in-state that you feed a scattering experiment is in fact entangled? So you can resolve without worrying about three. There's obviously need for further discussion of three as well. But one way to resolve that inconsistency between 1 through 3 is by replacing commitment number 2 with this observation we've just made, which is that microcausality implies cluster decomposition at the level of S matrix elements for very specific in and out states, which are not entangled. Okay, that's what you've actually been given an argument for here, not that it just works for any arbitrary matrix element that can be represented on the state space of the theory at all, which is how I initially stated too. So that collection, 1, 2 prime, and 3 is consistent much, and obviously there's we need to say more about 3 eventually as well. So now that reading of what's going on in this tension leaves open what happens to cluster decomposition in the cases where the in state does happen to be entangled. In those cases, I just want to point to 2 options here, and then we can talk about which, if any of these are the right way to think about what will happen in these cases. But here's one option, is just to say that if there is entanglement between spatially far separated clusters, there's no respect in which we really have 2 distinct clusters. There's something, if we feed an entangled in state and then we do this operation of translating, because we've left the entanglement in, whether it be in momenta or the spins, there's just something about the notion of what it is to be a cluster that's operative in this principle that we're trying to express, which we've run afoul of in allowing for that entanglement to be present. And then this worry goes away, and we can make sense of various expressions of the content of clustering in terms of the mathematical expressions I've already given you. Another option is to say that cluster decomposition is only supposed to be a prohibition on specific sources of failures of independence. So you might try to say something like the following. You might try to say, look, what I meant by cluster decomposition, what would amount to a violation of cluster decomposition would be if the Hamiltonian of the world turned out to be one of these Hamiltonians that doesn't satisfy whatever the analog of the necessary analog of Weinberg's sufficient condition turned out to be. Okay, something specific about, say, the nature of the dynamics, and you might be able to produce long-range dependencies in the theory by some mechanism other than that. But that doesn't amount to a violation of the principle that I'm trying to articulate when I articulate cluster decomposition. If it does turn out that entanglement is a problem for clustering, that's something you could say, which is that that's just not part of what I was trying to get at when I was expressing this principle. It's like not part of the content of the notion at hand. So there's obviously going to be other readings you could give. Those are just the 2 that we've been toying with for the moment, and I won't say that we're convinced by either of them yet. But if either of those, just for the sake of argument, grant that either one of those readings turned out to be right, I think they amount to what seemed to us at least to be pretty significant addenda to what the content of the cluster decomposition principle is supposed to be at all, what it's supposed to be telling us. And if the principle in question requires addenda of those sort in order to be fully articulated, then which reading we adopt here seems directly relevant for how we're supposed to understand which motivation for cluster decomposition is a compelling one, say, or which physical understanding of the principle we should adopt. And I will leave off there. Thank you very much.